Imagine this. You're a German soldier huddled in a foxhole somewhere in the Ardennes Forest. It's mid-December 1944, and winter has clamped down hard. You've survived Normandy. You've endured the grinding retreat through France. You know artillery. You know how it sounds, how it works, how to survive it. When you hear the whistle of incoming shells, you duck low, press yourself into the frozen earth, and wait for the impact. The explosion comes from below or beside you, maybe close enough to spray dirt, but if you're dug in deep enough, you'll probably walk away. But then, something changes. A new sound cuts through the air, not the familiar whistle, but shells that seem to arrive faster than you can register. And then, instead of hitting the ground, they detonate 30 feet above your head. The sky itself erupts in fire and steel. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Shrapnel rains down at angles no foxhole was designed to stop. Men around you scream. Some don't make a sound at all. Your log-reinforced bunker, the one you spent hours building, the one that saved you from direct hits before, offers no protection. The fragments slice through timber and earth like paper. And here's the part that makes your blood run cold. You never saw it coming. The shells gave no warning. They didn't need to hit anything. They just knew when to explode. That was the nightmare the Wehrmacht faced when American forces began using the proximity fuse. It wasn't just another artillery shell. It was a weapon that rewrote centuries of defensive tactics in a matter of seconds. For German troops who had grown used to artillery, who understood how to dig in and survive barrages, this was something entirely new. Reports from prisoners captured after the Battle of the Bulge described men refusing to leave their bunkers during artillery attacks. Not because the bunkers offered safety, but because moving meant certain death, and staying meant only probable death. The choice itself was a kind of madness. One captured officer admitted his men had stopped believing they could survive American artillery. They called it the shells that think. Here's the shocking truth. While the Germans had spent the war perfecting timed fuses and impact detonators, the Americans had developed something that seemed like science fiction. A tiny radar transmitter, no bigger than a milk bottle, crammed into the nose of an artillery shell. It could withstand being fired from a cannon at forces 20,000 times stronger than gravity. It could spin at 30,000 revolutions per minute without failing. And when it got close enough to the ground or a target, it simply knew to explode. The Germans never saw it coming because they thought it was impossible. Their own scientists had concluded that the mechanical stresses of artillery fire would destroy any electronic device delicate enough to function as a radar. So when their soldiers started dying in ways that made no sense, when shells began exploding overhead with uncanny precision, they assumed the Allies had somehow achieved perfect artillery timing, or that American spotters had become supernaturally accurate. They were wrong. What they were facing was a weapon that symbolized everything the Third Reich had underestimated about Allied industrial and scientific power. And by the time German intelligence captured samples and realized what they were dealing with, it was far too late. The proximity fuse had already changed the war. So today, we're diving deep into the full story. How this seemingly impossible device came to be. How American scientists solved problems that had stumped the British and Germans alike. How it turned the tide at the Battle of the Bulge. And why German soldiers, many of them veterans of years of brutal combat, found themselves helpless against shells that exploded 30 feet above their heads. Strap in, because this isn't just about technology. It's about a weapon so devastating that General George Patton called it the funny fuse and credited it with winning the Battle of the Bulge. It's about the moment when 20th century warfare took a quantum leap forward, and one side had it while the other didn't even believe it could exist. Back in 1939 and 40, artillery had a fundamental problem that had plagued gunners for centuries. To hit a moving target like an aircraft, or to maximize damage against troops in trenches, you needed shells to explode at precisely the right moment. Miss by even a second, and a shell would harmlessly overshoot or bury itself in the ground. The British had been the first to seriously pursue a solution. Their scientists knew that German bombers would be a deadly threat in any coming war, and traditional anti-aircraft guns had abysmal hit rates. Some estimates suggested it took 20,000 shells to bring down a single aircraft. At that rate, no nation could afford to defend its skies. The problem was mathematical as much as mechanical. An aircraft travelling at 300 miles per hour covered about 440 feet every second. A shell fired at that aircraft took anywhere from 10 to 30 seconds to reach altitude, during which time the target had moved thousands of feet. Gunners had to predict not just where the aircraft was, but where it would be when the shell arrived. Factor in wind, altitude changes, evasive maneuvers, and the sheer chaos of combat, and you had a problem that bordered on unsolvable. The British Royal Navy had been wrestling with this since the First World War, when Zeppelins and primitive bombers demonstrated that the age of aerial warfare had arrived. By the mid-1930s, several British scientists had independently begun thinking about proximity detection. William Butemont, working for the War Office, had actually proposed a radio-based proximity fuse as early as 1931. His idea was elegant. Use a small transmitter to send out radio waves, detect the reflection when the wave bounced off a target, and trigger the explosive when the reflection indicated close proximity. But the War Office dismissed the idea. The technology seemed too complex, too expensive, and too unreliable for practical military use. Butemont was told to focus on other projects. It wasn't until the late 1930s, with war looming, that the British revisited the concept. Samuel Curran, a physicist at the University of Cambridge, began working on photoelectric fuses for bombs and rockets. These used light sensors to detect changes in illumination as a bomb approached the ground. The principle worked in laboratory conditions, but in the field, results were inconsistent. Clouds, smoke, and the angle of the sun all affected performance. Acoustic fuses, which triggered when they detected engine noise, were even worse. They couldn't distinguish between friendly and enemy aircraft, and in the chaos of battle, background noise rendered them useless. So British researchers, including William Butemont and Samuel Curran, began exploring ways to make shells smarter. The concept was simple, in theory. Instead of requiring a direct hit, what if a shell could detect when it was close to a target and detonate automatically? But the execution was another matter entirely. Early ideas included optical sensors that would trigger when they detected a reflection, or acoustic devices that responded to engine noise. All of these suffered from the same problems. The electronics were too large, too fragile, and too unreliable for military use. By 1940, when France fell and Britain stood alone, the urgency became overwhelming. The Royal Air Force was fighting for survival during the Battle of Britain, and the Blitz was beginning to pulverize British cities. If German bombers could operate with near impunity, the war might be lost before it truly began. But the British, despite their brilliance, had hit a wall. They simply didn't have the industrial capacity or the specialized components needed to make a working proximity fuse that could withstand the violence of being fired from a gun. Then came one of the most consequential moments of the war. In September 1940, a British scientific mission led by Henry Tizard arrived in the United States carrying some of Britain's most closely guarded secrets. Among them were plans for cavity magnetrons, which would revolutionize radar, and preliminary work on proximity fuses. The Americans, who weren't yet in the war but were ramping up their defenses, saw the potential immediately. The United States Navy, in particular, was desperate for better anti-aircraft weapons. Japanese carrier aircraft were a rising threat in the Pacific, and the Navy's primary defense, the 5-inch 38 caliber gun, was only as good as its fuses allowed. In June 1940, even before the Tizard mission arrived, the National Defense Research Council had been formed under Vannevar Bush. This organization would coordinate civilian scientists to develop weapons for the military, and one of its first priorities became the proximity fuse. The job fell to a group called Section T, led by physicist Merle Tuve at the Department of Terrestrial Magnetism, part of the Carnegie Institution in Washington. Section T's mission was clear: make a proximity fuse work and make it work in time to matter. Tuve and his team understood the magnitude of the challenge. They needed to cram a working radar system into a space smaller than a soda can. It had to survive being fired from a cannon, which meant enduring acceleration forces of 20,000 times gravity. It had to spin at rates that would rip most machinery apart. It had to function in temperatures ranging from 100 degrees Fahrenheit to 50 degrees below zero. It had to be powered by a battery that could sit on a shelf for months and then activate instantly when the shell was fired. And it had to be cheap enough to mass-produce by the millions. If even one of these problems couldn't be solved, the entire project would fail. The pressure was immense. By early 1941, German U-boats were strangling Britain's supply lines, and Japan was expanding aggressively in Asia. American entry into the war seemed inevitable, and when it came, the country would need every technological edge it could muster. The proximity fuse wasn't just a nice idea, it was a necessity. And so, in labs and workshops scattered across the East Coast, scientists began the painstaking work of turning theory into reality. When Section T took on the proximity fuse project, they were starting from almost nothing. The British work provided a foundation, but translating that into a functional weapon was like trying to build a fighter jet using bicycle parts. The core concept was sound. The fuse would contain a miniature radio transmitter that sent out a continuous signal. When the shell got close to a target, whether an aircraft or the ground, the signal would reflect back. A receiver in the fuse would detect this return signal, and when the intensity reached a certain threshold, it would trigger the detonator. Simple in principle, nightmarishly difficult in practice. The scale of the engineering challenge cannot be overstated. Consider what had to happen in the fraction of a second between firing and detonation. The shell left the gun barrel traveling at speeds up to 2,600 feet per second. In that instant, it experienced acceleration forces of 20,000 times gravity. To put that in perspective, a modern fighter pilot might experience 9 times gravity in a hard turn. An astronaut during a rocket launch experiences about 3 to 4 times gravity. The proximity fuse had to survive forces more than 2,000 times what a human body could withstand, and it had to do so while maintaining the precise calibration needed for its electronics to function. The first major obstacle was the vacuum tubes. In 1940, all radio equipment depended on vacuum tubes, delicate glass components that amplified electrical signals. Standard radio tubes were designed to sit in a cabinet and operate gently. They were not designed to survive being fired from a cannon at speeds exceeding 2,000 feet per second. The initial acceleration alone would shatter them. Even if they somehow survived that, the centrifugal forces from the shell's spin would tear them apart. The shells spun at rates approaching 30,000 revolutions per minute. This was necessary for gyroscopic stability to keep the shell flying straight and true, but it created centrifugal forces that pulled outward on every component with thousands of times the force of gravity. The filaments inside vacuum tubes, normally hair-thin wires suspended in a vacuum, would be ripped from their moorings. The glass envelopes would crack, the seals would fail. Engineers at Western Electric and Raytheon set to work modifying miniature hearing aid tubes, the smallest vacuum tubes available, to withstand these forces. They reinforced the internal elements, changed the way the tubes were sealed, and tested them again and again. The solution involved redesigning the tubes from the ground up. Filaments were made thicker and shorter to resist the pull of centrifugal force. Glass envelopes were reinforced and shaped to distribute stress more evenly. New sealing techniques were developed to prevent the vacuum from leaking even under extreme vibration. And every modification had to be tested by actually firing the tubes from guns, recovering them, and examining whether they still worked. Thousands of test firings were conducted at Aberdeen Proving Ground in Maryland and at Kirtland Air Force Base in New Mexico. By January 1942, they had a tube that worked 52% of the time. The Navy accepted that failure rate. It wasn't perfect, but in war, a weapon that worked half the time was better than no weapon at all. The next problem was power. A proximity fuse needed electricity to operate, but it couldn't have wires running back to the gun. It needed a self-contained battery that could activate the moment the shell was fired. Standard batteries wouldn't work because they degraded over time or failed in extreme temperatures. Section T's solution was ingenious. They designed a liquid battery using a glass tube filled with electrolyte solution. When the shell was fired, centrifugal force pushed the liquid outward, bringing it into contact with metal electrodes. A chemical reaction began instantly, generating electrical current. This reserve battery, as it was called, solved the power problem and gave the fuse a shelf life measured in years instead of weeks. Then there was the antenna. A radar system needs an antenna to transmit and receive signals, but an artillery shell is a cramped, spinning projectile. Engineers realized they could use the nose of the shell itself as an antenna by placing a small metal cap at the very front of the fuse. As the shell spun through the air, the antenna spun with it, sending out a rotating radio beam. This created a kind of spiral search pattern that swept the area ahead of the shell. When the beam hit something solid, whether an aircraft or the ground below, the echo came back, and the fuse knew to detonate. Every component had to be miniaturized. The entire fuse, including the transmitter, receiver, battery, safety mechanisms, and detonator, had to fit into a cylinder about 8 inches long and 2 inches wide. This was decades before transistors or microchips. Everything had to be done with vacuum tubes and mechanical switches, soldered together by hand in an era when electronics were still something of an art. By mid-1942, Section T had a working prototype. It was called the Mark 32 fuse, and it was ready for testing. In August 1942, the Navy brought the cruiser USS Cleveland into Chesapeake Bay for a trial. Radio-controlled drone aircraft were launched to simulate enemy bombers. The Cleveland's 5-inch guns loaded shells with the new fuses and opened fire. The test was supposed to last 2 days. It ended on the first day because all 3 drones were destroyed with just 4 shots. The proximity fuse worked. For the scientists and engineers who had poured 18 months of their lives into the project, the relief was overwhelming. For the Navy, it was a revelation. Anti-aircraft gunnery had always been a gamble, a matter of throwing enough metal into the sky and hoping something connected. Now they had a weapon that could turn near misses into kills. But there was a catch. The proximity fuse was so valuable and so secret that using it would risk the enemy capturing a dud and reverse engineering the technology. For the next year, its use would be restricted to over open water, where failed fuses would sink beyond recovery. The secrecy surrounding the proximity fuse was extraordinary, rivaling that of the Manhattan Project. Workers were compartmentalized so thoroughly that most never understood what they were building. Assembly line workers in one factory might produce the glass vacuum tubes. Another factory made the battery components. A third assembled the mechanical safety mechanisms. None of them saw the complete fuse or understood how the pieces fit together. Security officers conducted regular sweeps to ensure no one was discussing their work. Letters home were censored. Visitors were forbidden. The mere mention of the word fuse outside of secure facilities could trigger an investigation. The scale of production was itself a feat of American industrial might. By late 1943, more than 100 companies were involved in some aspect of fuse production. Sylvania Electric, which had started as a manufacturer of radio tubes, became the largest single producer of the miniature vacuum tubes that made the fuses work. Their factory in Ipswich, Massachusetts, operated around the clock, employing thousands of workers, predominantly women, who assembled the delicate components by hand. Each tube had to meet exacting standards. Even a microscopic crack in the glass or a filament misaligned by a fraction of a millimeter could cause a fuse to fail. The Crosley Corporation, better known for manufacturing radios and refrigerators, retooled its facilities to produce complete fuse assemblies. General Electric plants in Schenectady and Bridgeport joined the effort. Eastman Kodak, RCA, and McQuay Norris all became major contractors. Even Wurlitzer, famous for its organs and jukeboxes, contributed to early production runs. The diversity of manufacturers meant that if one plant was bombed or suffered a breakdown, others could pick up the slack. It was redundancy by design, a lesson learned from watching German industry crumble under Allied bombing. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By late 1943, production had ramped up to 40,000 fuses per day. By the war's end, over 22 million had been manufactured. The cost per unit dropped dramatically as production scaled up. In 1942, a single fuse cost $732, an astronomical sum. By 1945, through improvements in manufacturing and economies of scale, the cost had fallen to just $18. This made the proximity fuse not just effective, but affordable. American artillery batteries could use them freely, confident that the supply would never run out. The total cost of the program exceeded $1 billion in 1940s currency, equivalent to about $15 billion today. It was a massive investment, but one that paid dividends in lives saved and battles won. But the proximity fuse's greatest test was still ahead. It would prove its worth first in the Pacific, then in the skies over London, and finally on the frozen battlefields of Europe. And when it did, it would shatter the Wehrmacht's belief that they understood the limits of Allied firepower. The proximity fuse saw its first combat on January 5, 1943. The cruiser USS Helena was operating off Guadalcanal when 4 Japanese dive bombers attacked. One struck the New Zealand cruiser Achilles before the group began to withdraw. As an afterthought, Helena's anti-aircraft gunners fired a few salvos at the departing aircraft. 2 5-inch shells, fused with the new proximity detonators, exploded near one of the bombers without directly hitting it. The aircraft, shredded by shrapnel, tumbled into the sea. It was the first confirmed kill by a proximity fuse, and it validated everything Section T had promised. Over the next 2 years, the proximity fuse became standard equipment on American warships. Japanese pilots, already facing overwhelming American air defenses, found themselves up against a new level of lethality. Shells no longer had to hit them directly. A near miss was now lethal. Naval historians later estimated that proximity fuses increased anti-aircraft effectiveness by 3 to 4 times. In some battles, the kill ratio improved by 370% compared to timed fuses. During the final year of the war, as kamikaze attacks intensified, the proximity fuse became indispensable. Destroyers defending aircraft carriers used them to create walls of exploding shells that shredded incoming suicide planes before they could reach their targets. The fuse also proved crucial against German Wohn flying bombs. In June 1944, Hitler began launching these pilotless rockets at London in a last-ditch effort to break British morale. The V-1s flew low and fast, making them difficult targets. Initially, British anti-aircraft guns destroyed only about 24% of them. Then, in a desperate gamble, the Allies authorized the use of proximity fuses over land for the first time. The risk of a dud falling into German hands was deemed acceptable given the stakes. Anti-aircraft batteries along the English coast were equipped with the new fuses, and the results were immediate. Within weeks, the interception rate climbed to nearly 80%. Of the thousands of V-1s launched, only a fraction reached London. The proximity fuse had saved the city. But it was the Battle of the Bulge that truly showcased what proximity fuses could do in ground combat. On December 16, 1944, German forces launched their last great offensive in the west, pouring through the Ardennes in a desperate attempt to split the Allied armies and capture the vital port of Antwerp. The weather was terrible, grounding Allied air power and giving German troops the mobility they needed. For the first few days, it seemed as though the offensive might succeed. American units were caught off guard, surrounded, and in some places overrun. The German plan, codenamed Watch on the Rhine, was audacious. 3 armies, more than 200,000 men, supported by hundreds of tanks and assault guns, would punch through thinly held American lines in the Ardennes Forest. The goal was to reach the Meuse River, cross it, and drive northwest to Antwerp, severing the Allied supply lines and forcing a negotiated peace in the west. It was Germany's last gamble, throwing reserve divisions and precious fuel stocks into one final offensive. And for the first 48 hours, it seemed to be working. American forces, many of them inexperienced or resting from earlier battles, were thrown into chaos. The German assault achieved complete tactical surprise. Communications broke down. Units were cut off. The weather prevented Allied aircraft from providing support. German panzers rolled through gaps in the line, and for a moment it looked as though Hitler's desperate plan might actually succeed. Towns like Bastogne became encircled strongpoints, their defenders clinging to road junctions that the Germans needed to sustain their raid. Advance. Then General Dwight Eisenhower made a decision that would change the course of the battle. Despite the Pentagon's strict orders to never use proximity fuses over land, Eisenhower demanded permission to unleash them. He argued that the emergency justified the risk, and he prevailed. Within 2 days, over 200,000 proximity-fused shells were rushed to American artillery batteries across the front. The code name was Posit, a deliberate misdirection to conceal their true nature. The logistics of getting the fuses to the front were staggering. Trains, trucks, and even special aircraft were diverted to rush crates of the secret weapons to artillery units scattered across Belgium and Luxembourg. Ammunition dumps that had been stocked with conventional shells were hastily resupplied. Battalion commanders were briefed on the fuses in hurried conferences, told only that these shells would detonate automatically at the optimal height and that under no circumstances should they allow a dud to fall into enemy hands. Security officers reminded gun crews that discussing the weapons outside of secure areas could result in court-martial. What followed was unlike anything the Wehrmacht had experienced. American artillery, already formidable, suddenly became devastating. Shells that would have buried themselves harmlessly in the snow now exploded 30 feet in the air, spraying shrapnel downward in lethal cones. German troops caught in the open were shredded. Foxholes and slit trenches, which had protected soldiers for generations, became death traps as fragments rained down from above. Even log-reinforced bunkers offered little safety. The high-velocity shells arrived faster than sound, meaning soldiers had no warning. One moment there was silence. The next, the air was filled with explosions and screaming metal. The effectiveness was beyond what even American commanders had anticipated. Artillery forward observers reported that single volleys of proximity-fused shells could clear defensive positions that would have required sustained bombardment with conventional ammunition. German counterattacks that formed up in wooded areas were shattered before they could even begin their advance. Supply columns moving at night, believing they were safe from observation, were caught in the open and annihilated. The airbursts proved particularly effective in the dense Ardennes forests, where shells detonating above the trees sent fragments down through the canopy to strike troops who thought they were concealed. General George Patton, whose Third Army wheeled north to relieve the besieged town of Bastogne, wrote a letter to the War Department describing the new shells. He called them devastating and credited them with annihilating German units caught in the open. In one engagement near the Sauer River, a battalion-strength concentration was hit by proximity-fused artillery. American forces counted 702 German dead. Patton concluded that when all armies get this shell, we will have to devise some new method of warfare. He was grateful the Allies had thought of it first. German prisoners captured during and after the Bulge described the psychological impact. Many said they had no defense against the airbursts. They couldn't dig deeper because the fragments were coming from above. They couldn't move because movement exposed them even more. They described feeling helpless, as though the very sky had turned against them. One officer told interrogators that his men emerged from barrages in a dazed state, unable to understand what had happened. Intelligence reports noted that some German units experienced what could only be described as a mutiny, with soldiers refusing to leave their bunkers even under direct orders. The effect wasn't just physical, it was moral. German troops had endured years of artillery fire. They had developed tactics, training, and mental conditioning to survive it. Now, suddenly, all of that was useless. The rules had changed, and they had no answer. By the time the Battle of the Bulge ended in late January 1945, the German offensive had failed utterly. While many factors contributed to the Allied victory, the proximity fuse played an undeniable role. It had turned American artillery from a blunt instrument into a precision killer, and the Germans still didn't fully understand what they were facing. During the battle, they captured an American ammunition dump containing thousands of proximity-fused shells. German engineers examined them, but concluded they must be some kind of improved timed fuse. The idea that the shells contained miniature radar systems seemed absurd. After all, German scientists had studied proximity fuses since the 1930s and concluded that the stress of artillery fire would destroy any electronic device. Their own prototypes, based on acoustic and electrostatic principles, had never progressed beyond the experimental stage. The notion that the Americans had succeeded where Germany had failed was too much to accept. By the time German intelligence finally pieced together the truth, it was far too late. American factories were producing proximity fuses by the tens of thousands every day, and the Wehrmacht was in full retreat. The weapon that had seemed impossible was now everywhere, and there was nothing Germany could do about it. As the winter of 1944 gave way to spring 1945, the proximity fuse continued to rewrite the battlefield. American forces pressed into Germany itself, crossing the Rhine and advancing toward the heart of the Reich. At every step, proximity-fused artillery paved the way. German strong points that might have held out for days were reduced in hours. Troop concentrations were devastated before they could even form up for counterattacks. The psychological toll was immense, and it showed in the rapidly deteriorating morale of German units. What made the proximity fuse so terrifying was its versatility. Against aircraft, it turned every shell into a potential kill. Against ground targets, it functioned as an area denial weapon, making entire stretches of terrain untenable for defending forces. And because the shells exploded in mid-air, they cut communication wires and disrupted radio transmissions far more effectively than ground impact explosions. German officers found it increasingly difficult to coordinate defenses when their command networks were constantly being severed by overhead detonations. The fuse's design also made it ideal for hitting targets that traditional artillery struggled with. Soldiers on the reverse slopes of hills, hidden in forests, or dug into fortified positions all became vulnerable. Forward observers didn't need to see the target directly. They just needed to know the general area. The proximity fuses would do the rest, detonating at the optimal height to maximize damage. This meant that American artillery could suppress or destroy targets even when visual observation was impossible, a massive advantage in the close terrain of the Rhineland and southern Germany. For German troops, the sense of being hunted from above by an invisible, inescapable weapon was demoralizing beyond measure. Veterans who had survived Stalingrad and Normandy described the proximity-fused barrages as worse than anything they'd faced before. At least against bombers or conventional artillery, you could take cover and have a chance. Against shells that exploded overhead, there was no safe place. The only option was to scatter and hope. By March 1945, proximity fuses had also been adapted for use in aerial bombs. American bombers began dropping proximity-fused munitions on German anti-aircraft positions. The results were devastating. Flak batteries that had tormented Allied air crews for years were silenced in minutes. The bombs would detonate just above the guns, showering them with fragments and making it impossible for crews to operate. In northern Italy, in April 1945, B-24, liberators used proximity-fused bombs to clear corridors through German defences, allowing follow-on bomber formations to pass through unmolested. The Japanese also faced the fury of proximity fuses in the Pacific. During the Okinawa campaign, kamikaze attacks reached their peak intensity. American destroyers and carriers came under relentless assault from waves of suicide planes. But the proximity fuse gave the fleet a fighting chance. In one notable engagement, the destroyers USS Hadley and USS Evans faced over 150 Japanese aircraft in 90 minutes. Using proximity-fused anti-aircraft shells, they shot down dozens before finally being overwhelmed. Both ships survived, battered but afloat, and the battle became a testament to how effective the fuse was even under the most extreme conditions. By the time Germany surrendered in May 1945, the proximity fuse had fundamentally altered the calculus of warfare. It had proven itself in every theatre, against every type of target, under every conceivable condition, and it had done so while remaining largely a mystery to the enemy. Even after the war, captured German scientists expressed disbelief when they learned the full details of how the fuse worked. Many admitted they had assumed it was impossible and had given up trying. The legacy of the proximity fuse extended far beyond World War II. Its principles would inform the development of guided missiles, smart munitions, and modern air defense systems. But in those final months of the war, it was simply a weapon that gave the Allies an edge no amount of courage or tactics could overcome. For the Wehrmacht, already facing overwhelming odds, the proximity fuse was the final proof that this was a war they could not win. For German soldiers who lived through proximity-fused barrages, the experience left scars that went beyond the physical. Interviews with prisoners of war and post-war interrogations paint a consistent picture. Men described feeling utterly helpless, a sensation that was alien to troops who had been trained to believe in their own discipline and resilience. One captured sergeant told American intelligence officers that the airbursts were like fighting ghosts. You couldn't see them, couldn't predict them, couldn't defend against them. Another soldier said his unit had started calling them the shells that think, a name born from the eerie accuracy with which they seemed to know exactly when to detonate. The psychological damage manifested in ways that surprised even veteran interrogators. Some prisoners were visibly shaken when discussing the weapon, their hands trembling as they described how quickly entire squads had been wiped out. Others displayed a fatalistic resignation, as though they had accepted that modern war had simply become unwinnable for Germany. A few expressed anger, not at the Americans, but at their own leadership for failing to develop similar weapons. They felt betrayed by promises of wonder weapons that never materialized, while the enemy deployed technologies that seemed pulled from science fiction. German officers faced a different kind of torment. They had been trained to analyze threats, develop countermeasures, and adapt tactics to battlefield realities, but against proximity fuses, there were no effective countermeasures. Orders to dig deeper were useless when the threat came from above. Dispersing troops reduced casualties but made coordinated defense impossible. Staying in bunkers turned men into sitting targets. Every tactical choice seemed to lead to the same outcome: death or surrender. Some officers privately admitted that the arrival of proximity-fused artillery marked the moment they knew the war was truly lost. What made the situation worse for the Germans was that their own proximity fuse research had been abandoned years earlier. In the early 1940s, Rheinmetall Borsig and other firms had explored acoustic, electrostatic, and even radio-based designs. Some prototypes showed promise, particularly an electrostatic model that could detect the electrical field of an aircraft. But in 1940, Adolf Hitler issued a directive that halted all weapons research that couldn't reach production within 6 months. The proximity fuse, still plagued by technical problems, was shelved. Resources were diverted to projects deemed more immediately useful, like improved tank guns and rocket artillery. By the time German scientists realized the Americans had succeeded, it was far too late. Even if they could reverse engineer a captured fuse, Germany lacked the industrial capacity to mass produce it. The miniature vacuum tubes alone required specialized manufacturing processes that German factories, by 1945, could no longer sustain. The electronics industry that had once been world-class was now crippled by bombing, resource shortages, and the chaos of a collapsing regime. Interrogations of Reichsmarschall Hermann Göring after the war revealed that German scientists believed they could have had a working proximity fuse in production within 3 to 4 months if given the resources. But those months and those resources no longer existed. For the soldiers on the receiving end, these technicalities meant nothing. All they knew was that American shells exploded in ways that defied logic, and that their chances of survival diminished with every barrage. Reports from the Ardennes Forest, the Bulge, and the Rhineland all described the same phenomenon: Men emerged from proximity-fused attacks looking as though they had been through a meat grinder, one chief ordnance officer wrote. Foxholes provided no protection, and even log-reinforced bunkers were penetrated by the shrapnel. German medics, already overwhelmed, found themselves treating wounds they had never seen before, injuries caused by fragments coming from overhead at oblique angles that conventional artillery couldn't achieve. By the final weeks of the war, entire German units were refusing to hold positions that came under proximity-fused bombardment. Desertions increased, surrenders became more common. American forward observers began to notice that a few volleys with the new fuses could clear a defensive line that might have taken a full assault to dislodge just months earlier. The weapon had become not just a tool of destruction, but a psychological hammer that broke the will to resist. And through it all, the Germans never fully grasped how the fuses worked. Some believed the shells used magnetic sensors to detect helmets or weapons. Others thought they were triggered by body heat or the electrical activity of the human nervous system. A few concluded that American forward observers must have gained some supernatural ability to time their shots perfectly. The truth, that each shell carried a miniature radar system capable of withstanding forces that should have pulverized it, remained beyond their comprehension. To men raised in a world where radios were still bulky, furniture-sized devices, the idea of a radar set smaller than a milk bottle simply didn't compute. In the end, the proximity fuse did more than kill German soldiers. It killed their confidence, their belief in their own technological prowess, and their hope that the war could be turned around. It was a weapon of the future deployed against an enemy still fighting with the mindset of the past. And for those who faced it, the memory of shells exploding 30 feet overhead would haunt them for the rest of their lives. The proximity fuse didn't end with World War II. Its influence echoed through every conflict that followed. During the Korean War, American forces once again used proximity-fused artillery to devastating effect against Chinese and North Korean troops. The mountainous terrain made traditional artillery less effective, but airburst shells turned valleys and ridgelines into killing zones. Communist forces, unprepared for the technology, suffered catastrophic casualties in the opening months of the war. They adapted eventually, dispersing their forces and moving under cover of darkness, but the psychological impact lingered. In the decades after the war, the proximity fuse evolved. The bulky vacuum tubes gave way to transistors, then integrated circuits. Modern proximity fuses are smaller, more reliable, and far more sophisticated than their World War II ancestors. Today's artillery shells, missiles, and bombs use a variety of sensors, laser rangefinders, radar, and even GPS to determine the optimal moment to detonate. But the core principle remains unchanged. Strike when close, maximize lethality, give the enemy no place to hide. The proximity fuse also paved the way for guided munitions. If a fuse could detect proximity and trigger a detonation, why couldn't it also adjust a weapon's flight path? This line of thinking led to the development of air-to-air missiles, surface-to-air missiles, and eventually precision-guided bombs. The Phoenix missile, the Standard Missile family, and the Patriot air defense system all owe a debt to the wartime proximity fuse. Even modern anti-tank weapons like the Top Attack, Javelin use proximity sensors to detonate above armored vehicles, striking their weakest point. For historians, the proximity fuse stands as one of the most significant innovations of the 20th century. It's often compared to radar and the atomic bomb in terms of impact, and rightly so. While the atomic bomb ended the war, the proximity fuse helped win it. Admiral Lewis Strauss called it one of the most original and effective military developments of the war, and Vannevar Bush credited it with 3 critical contributions: drastically improving anti-aircraft defense, enabling effective ground artillery against fortified positions, and providing a technological edge that the Axis powers could not match. But perhaps the most telling legacy is what it represented. The proximity fuse was a triumph of American industrial mobilization, scientific ingenuity, and cross-disciplinary collaboration. It brought together physicists, engineers, manufacturers, and military planners in a way that few projects had before. It required innovations in miniaturization, materials science, and mass production that would influence civilian technology for decades. The printed circuit boards used in the fuses were among the first ever mass-produced, a precursor to the electronics revolution that would define the latter half of the century. For the Germans who faced it, the proximity fuse became a symbol of why they lost the war. It wasn't just that the Allies had more tanks or more planes or more men. It was that the Allies could conceive of, develop, and deploy technologies that seemed impossible, and do so at a scale that defied comprehension. 22 million fuses produced in less than 3 years. Over 100 factories coordinated to manufacture components. Thousands of scientists and engineers solving problems in parallel. It was an exhibition of industrial and intellectual power that Nazi Germany, for all its vaunted engineering prowess, simply could not match. Today, the proximity fuse is a footnote in many histories, overshadowed by more dramatic weapons. But for the men who served, it was unforgettable. American artillerymen spoke of it with pride, knowing they wielded a weapon that their enemies feared and respected. German soldiers remembered it with a mix of dread and grudging admiration, and the engineers who built it carried the knowledge that their work had saved countless Allied lives and hastened the end of the most destructive war in history. In the frozen forests of the Ardennes, on the Pacific atolls where kamikazes fell from the sky, in the ruins of German cities where V-1s were blasted from the air, the proximity fuse proved its worth. It was a weapon that thought, that adapted, that killed with a precision that earlier generations could only dream of. And for the Wehrmacht, who never imagined artillery shells would explode 30 feet above their heads, it was the beginning of the end. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.